Hello. There is an interesting problem called the defective chessboard problem that is useful in illustrating the idea of divide and conquer. It's also interesting that there is no intuitive or obvious solution to the problem of a defective chessboard, but divide and conquer gives us a neat and elegant solution to the defective chessboard problem. So what is this defective chessboard and what's the problem? Right? So you are given a chessboard of size n by n, where n is a power of 2. So you have 2 to the power of k rows and 2 to the power of k columns, right? And what we are also given is that exactly one square in this chessboard is defective. It may be anywhere on the chessboard, but one of the squares is defective. All the others are not defective. And what we need to do is cover the chessboard completely with a set of L-shaped tiles, right? So these L-shaped tiles are called trominos, but somehow the textbook calls it triominos. So whether we call them trominos or triominos is really not significant. These L-shaped tiles are made up of 3 squares, and they have one of these shapes. So it can be this, or this, or this, or this. So as you can rotate them and see, these are the only 4 possibilities for L-shaped tiles. So how do we, given a large chessboard of size n by n, where n is a power of 2, how do we solve this problem of covering the entire chessboard with these L-shaped tiles, leaving the one defective square out? Now, is that always possible? You may wonder. Why is it possible? Why is there always a solution? This is a simple mathematical analysis we can do to convince ourselves that there is always a solution to this problem. We are told that the number of square is n into n, n squared. And n is a power of 2, so that happens to be 2 to the power of k multiplied by 2 to the power of k, which is 2 to the power of 2k. And the number, there's one defective square, so the number of non-defective squares is 2 to the power of 2k minus 1. That is 2 raised to an even power and 1 less than that. That number is always divisible by 3. Why is that? Well, you can actually do a proof by mathematical induction, but we'll just look at a few examples. So if k is 0, right, then you have the number of squares to be tiled is 0. If k is 1, then the number of squares to be tiled is 3. So it is possible to cover 3 tiles with a L-shaped tile. If it is 2, that means this is 15, which is again divisible by 3. If it is 3, we are talking about 2 to the power of 6 minus 1, 63, which is again divisible by 3. So all of these numbers are divisible by 3. So it is going to be possible to always cover them with these tiles made up of 3 squares each. Right? We assume that we have a sufficient number of tiles of each of these, and they can be rotated into any of the 4 possible positions. So we do have a sufficient number of tiles to cover this. So how does it work? What is this problem? If you look at the simplest instance of a 1 by 1 chessboard, defective chessboard, then that square itself is defective. We are going to show defective squares by coloring them dark black. Right, so this square itself is defective, so there is no tile to be added. This problem is already solved. So the 1 by 1 defective chessboard is already tiled. The 2 by 2 defective chessboard, right, can have one of these. There are 2 more possibilities, right? The defective square can be here or here as well. But in any case, there is 1 defective squares and 3 non-defective squares. So these squares can be, this can be covered with an L-shaped tile, or this can be covered with an L-shaped tile, and so on. So there are obvious solutions for the 2 by 2 case. Next we look at 4 by 4, right? When you have a 4 by 4 defective chessboard, and here are two examples, you will have 16 such defective chessboards, depending on which of the squares is defective. Then is it possible to cover them, right, with a L-shaped tiles? For example, the only possibility here is, because of the defective square, is to cover it that way, right? Then there exists a solution, but we have to be careful in choosing that. So I can do this and then do that. right? And then this, and then, right? That was not very colorful. We'll use colors later to show how it works. But it is possible to color. So essentially we found one tile like that, one like that. The others are obvious, right? So one like this, and one like this, and one like that. So it is possible to cover this 4x4 defective chessboard with 1, 2, 3, 4, 5 L-shaped tiles. That is 5 times 3 is 15 squares and 1 defective square. So totally there are 16 squares. Similarly, for all the defective chessboards, it is always possible to cover them with those triominoes or trominos, the L-shaped tiles. So how do we apply a divide and conquer solution? What is an algorithm for solving this problem? The size k equals 1 2 by 2 problem has a simple solution as we saw. One square is defective. There are only 3 remaining squares. We cover it with a single tile and the problem is solved. If we are given a larger chessboard, larger defective chessboard, we simply divide it into smaller ones. And then we solve the smaller ones and then we combine the solutions for the smaller ones. But it's not quite that simple. There is a catch, as we will see. So here is an 8 by 8 defective chessboard. So it has 64 squares and exactly one square is defective, the one shown in black. The remaining 63 squares have to be covered with L-shaped tiles. So I don't know how to solve this directly. I'm going to apply the divide and conquer method. I'm going to divide this into 4 smaller problems, right? So these were 8 by 8 boards. Now I have 4 by 4 boards, right? But there is a problem. The problem that I started solving was a defective chessboard problem. This particular 4 by 4 instance is actually a defective chessboard problem. The other 3 are non-defective chessboard problems. There is no defect in the other 3 4 by 4 chessboards, right? So I can't simply apply the same algorithm. In fact, it is not possible to cover a 4 by 4 non-defective chessboard with L-shaped tiles because it has got 16 squares. 16 is not divisible by 3, so I am never going to be able to cover all of it. So how do we solve this problem? We need a trick to make sure that the smaller problem is of the same kind as the larger problem. The larger problem was a defective chessboard problem where exactly one square was defective. Now how do I make the smaller squares, the smaller problems, also defective chessboard problems? And the trick we do is we artificially introduce defects in all those 3 of them while ensuring that it is still possible to tile them. And that trick is exactly this. By making these 3 squares defective, right? Now I have made sure there are 2 things are possible. One is all the 4 sub-problems are also defective chessboard problems in the sense they have exactly one defective square, right? So we are going to show artificially introduced defective squares by coloring them dark gray. The original defective square is still black, right? So by coloring these now, I have made sure that each of the 4 by 4 problems is also a defective chessboard problem, and by putting these 3 defective squares in an L shape, I have made sure that they themselves can be covered by a single tile, right? Because the original objective is to cover all the 63 tiles except that one defective square. So now that is possible because I am going to arrange the defective squares, the artificially introduced defective squares in the sub problems in this L shape. Next, what do? I don't know how to solve a 4 by 4 defective square problem, so I am going to divide that further into a 2 by 2 defective square problem. So now we have 16 2 by 2 defective squares. Once again, you will see that I have artificially introduced L-shaped defective squares, 3 defective squares, whenever the 4 by 4 problem was broken into the 2 by 2 problems, right? So all of them can be covered by tiles. So now we have 16 sub-problems, each of which is a 2 by 2 defective square problem. I know how to solve them. So I never really had to figure out how to solve an 8 by 8 defective square problem. I simply have to defective chessboard problem. I simply divide it into smaller and smaller problems. Now I am left with 16 2 by 2 problems which I know how to solve. Let's just go ahead and solve them. Right? So I'm going to color that tile red, this one blue, this one yellow, this one green. I'm just trying to make it colorful so we can distinguish one L-shaped triomino from another. So now we have solved these 4 2 by 2 problems. I need to combine them. Divide and conquer always involves dividing, solving the subproblems, and then combining the solutions to the subproblems. So if I combine the solutions to those 4 subproblems, I need to obtain a solution for the original 4 by 4 problem that I had. Right? This entire set of squares need to be tiled, and to do that I need to do this additional thing. So coloring these 3 artificially introduced defective tiles with that purple colored tile was the combination part. So now I have solved one 4 by 4 defective chessboard problem. We continue and solve the other ones. So there is red, blue, yellow, and green. You see that the yellow here and the yellow there are rotated in different positions. That depends on the position of the defective square in that particular instance. So now again I have to combine those 4 solutions by adding this tile in the middle. So now we have solved 2 of the 4 by 4 problems. We continue red, blue, yellow, green, and then combination purple, and then once again red, blue, yellow, green, and the combination purple. So now I have solved 4 4 by 4 defective chessboard problems. I need to combine those solutions to obtain the solution to the 8 by 8 defective chessboard problem. How do we combine? We need to take care of this L-shaped tile in the middle, which spans across the three of the 4 defective 4 by 4 problems. So by coloring that tile as well, now we have colored the entire 8 by 8 defective chessboard. Only the one black square which was defective is left untiled. All the other tiles, as you can see, are L-shaped triominos. So that is a wonderful divide and conquer solution for the defective chessboard problem. You may wonder, why should we really care about this defective chessboard problem? It is just a useful problem in understanding and illustrating the divide and conquer technique. We will not actually bother to write down the pseudocode for the algorithm for this. It is fairly straightforward. You can write it yourself. We will also not do the analysis because this turns out to be a theta n square kind of an algorithm, which is reasonable because there are in fact order n squared tiles, and each tile needs square, and each square needs to be tiled. Right? So and each square is tiled only once, so it is quite reasonable that this is an n squared algorithm. It can't be better than that, and it is not worse than that either. Each square is tiled only once, and each square must be tiled, so it is theta n squared. So that is the colorful defective chessboard problem and its divide and conquer solution. Thank you.